Okay, I think we should just get started. Welcome everyone who's tuning in. This session is virtual full paper VIS from around the world. We have 6 exciting papers for us to kind of listen to, presented by the researchers around the world. Without much delay, I think we will start with the first paper, which is FPCS, feature preserving compensated sampling of streaming time series data from authors Hongyan Li, Boyang, Yansong Chua, and the presenter is going to be Hongyan Li. Hongyan, take it away.
Okay, thank you. Hello everyone, I'm Hongyan Li. Today I will be presenting our work FPCS feature preserving compensated sampling of streaming time series data. This paper is collaborated by me, Boyang, and Yansong. I will present our proposed algorithm FPCS from 5 aspects. Firstly, I will introduce the background of our work and why we should care. What is streaming time series data? Actually, it contains streaming data and time series data. Streaming data is an infinite collection of dynamic data that grows over time. For streaming data, data arrives in real time. The scale of data is vast and unpredictable. Time series data is a collection of data recorded in chronological order. For time series data, data exhibits temporal dependency. Data is typically collected continuously or periodically. Presently, streaming time series data has seen increasingly widespread applications in fields such as biology, finance, and medicine. For massive and continuously growing streaming time series data, this data is typically visualized in the form of line charts. But the data transmission puts significant pressure on the network, leading to visualization lag or even failure to render completely. Therefore, we need to perform effective sampling. However, there is currently no research on similar algorithms for sampling streaming time series data. Therefore, in the second part, I will discuss the previous work on streaming data sampling and the time series data sampling separately. Sampling of streaming data includes reservoir sampling and those use sliding windows. The reservoir sampling algorithm is a type of random sampling that fails to achieve the goal of returning feature points. Many algorithms use sliding windows like generality or have poor retention of feature points due to random sampling. Sampling of time series data, including min-max M4, LTTB, and min-max LTTB. The min-max and M4 algorithms have large space complexity and the effectiveness of data sampling varies. The LTTB and min-max LTTB algorithms requires complex calculations, and during the selection of data points, points from adjacent buckets need to participate in the operation, indicating correlation among the data. So we aim to propose a completely new sampling algorithm. In terms of visualization effect, similar to the LTTB and min-max LTTB algorithms, it achieves good feature retention results. In terms of time complexity, similar to the min-max and M4 algorithms, it reduces a large number of complex calculations. In terms of space complexity, it leverages the advantages of streaming data, only catching a limited amount, controllable and finite data in memory, especially because it is processing streaming data. Whether a data point is returned cannot depend on the overall data. In the third part, I will describe the method of the FPCS algorithm. During the visualization process, extreme points form the key features of line charts. And over a continuous period, time series data typically exhibit fluctuating growing or decline trends. Therefore, in most cases, only the current maximum and minimum value point need to be considered during each sampling operation. Analysis reveals that in most cases, both max point and mean point do not need to be returned. To better fit the trend of the original data starting to change, Each sampling operation returns only the earlier received max point or mean point in the current interval. We analyze the 9 most common cases within a sampling interval. Only 2 conditions require returning 2 points: compensate for later received mean point or max point in the previous sampling interval, referred to as potential point, and return the earlier received max point or mean point in the current sampling interval. For all other conditions, it is sufficient to return only the earlier received max point or mean point in the current sampling interval. Therefore, the FPCS algorithm consists of the following steps. First, determine the sampling ratio. Second, initialize variables. Third, decide to update the max point or mean point based on the newly received data points. Fourth, when sampling is required according to the sampling ratio, determine whether to compensate for the potential point and return max point or mean point received earlier. The FPCS algorithm only maintains a few variables, so its base complexity is O1. The FPCS algorithm performs very few comparison calculations and assignment operations each time it receives a new data point, so its time complexity is On. In the first part, we verified the correctness, effectiveness, and the performance of the FPCS algorithm through extensive performance. The experiment selected the listed simulator, selected a membrane potential dataset. The experiment also used 5 typical datasets from the DEBS 2012 Grand Challenge and so on. A data point was randomly selected from the membrane potential dataset as the starting point. The experiment sampled 50,000 data points using the FPCS, reservoir sampling, LTTB, and min-max LTTB algorithms. The sampling ratio was set to 100:1. The FPCS algorithm returns effectively feature points completely and achieves the best visualization effect. The experiment sampled the first 100,000 data points from each of the 5 typical datasets using 4 algorithms. The sampling ratio was set to 100:1. The FPCS algorithm shows the best visual fitting effect between sampled data points and original data points, and the best retention results for feature points. We used 4 algorithms with sampling ratio of 100:1, 200:1, 500:1, and 1000:1 on 2 datasets. The membrane potential datasets with a capacity of 1 million and 5 typical datasets with a capacity of 100,000. From the perspective of SSIM, the FPCS algorithm consistently demonstrates the best sampling effect regardless of the situation. Experiments were conducted on the membrane potential datasets with a capacity of 100 million, incrementing by 10 million each time, under a sampling of 100:1. The result shows that regardless of the situation, the FPCS algorithm has the shortest execution time, regardless of the dataset size. The space usage is less than 0.1 megabyte, exhibiting the best space complexity performance. Finally, I will summarize our work. We propose a universal FPCS algorithm, which is the first to implement sampling for streaming time series data. Compared to other algorithms, the FPCS algorithm achieves the best visualization effect for returning feature points, fitting the visualized line chart of original data points best. In terms of time complexity, the FPCS algorithm does not involve complex calculations, resulting in the shortest algorithm execution time regarding space complexity, making the smallest algorithm execution space. Thank you so much for listening. Please refer to our paper to know more.
Thank you so much. It was really interesting to see kind of like the kind of sampling and how it relates to kind of streaming visualizations. Question-wise, I want to start with this one question. You mentioned that sometimes compensation has to be made to find the potential point. Can you please explain a situation where that might happen? When do we need to compensate for the potential point?
In fact, only 2 conditions need to compensate for a larger point means in one sampling interval need to return 2 points. Other conditions only need to return 1. So our algorithm need to compensate for the special cases. Only can improve our algorithms effective.
Thank you. Let me see if there are any other questions. One more question, like a follow-up question from my side, which is, what kind of applications do you think would benefit from this sampling method?
Oh, okay. For example, we can do some FPCS is to sample the sampling time series data. It can using the static and the stream time series data. For them, in some FPCS can be applied to visualize both static and stream time series data. For example, membrane potential data visualization of neurons.
All right. Thank you so much. Great talk. A round of virtual applause for Hongyan before we switch. Our next presentation is on uncertainty-aware deep neural representations for visual analysis of vector field data. The authors of this paper are Atul Kumar, Siddharth Garg, and Soumya Dutta. Atul is the presenter. However, due to some technical difficulties, Atul will not be able to speak up directly, and we're going to use a pre-recorded video for this particular talk. So I'm gonna go ahead and run the pre-recorded video now. Okay.
Hello everyone, I'm Atul Kumar from the Department of Computer Science and Engineering at Indian Institute of Technology, Kanpur. I am here to present our paper titled Uncertainty-Aware Deep Neural Representations for Visual Analysis of Vector Field Data. Implicit neural representations have become popular for modeling scientific data thanks to their success in multiple use cases. For example, neural network-based approaches produce state-of-the-art results in compression of large volumetric datasets. They manage to achieve an excellent reconstruction quality from those compressed representations. As a result, these implicit neural representations have several applications in scalar and vector data analysis. However, the problem with a deterministic model is that they don't provide any uncertainty information to its users. Without it, the reliability of the predicted results remain in question. For the scientists and experts in any scientific domain, lack of uncertainty information means a lack of trust on those deep learning methods. In a simple scenario, a neural representation acts as an efficient way to model complex vector field data. The ground truth data is available to us, and we use that to train and optimize a deep neural network. After the training finishes, the neural network acts as an implicit neural representation of the vector field. This INR model can then be used to perform many operations as if it were the data itself. Furthermore, the answers provided by the INR model can be tested for error and accuracy against the ground truth vector field data to establish its correctness. However, in many cases, the original ground truth data may not be retained due to the large size of the data and the model we used as a surrogate for it. In such cases, checking prediction accuracy is impossible since we do not have access to the ground truth data. But since the uncertainty estimate is an inherent property of the model, it can be estimated robustly in such cases. Uncertainty estimates can be interpreted as a measure of model's confidence in its predictions and can be very helpful to check the reliability and trustworthiness of the model's predictions. Hence, in this work, we advocate the use of uncertainty-aware INRs in place of deterministic INRs. A model would then be able to provide fine-grained uncertainty estimates along with the usual predicted values. After the uncertainty values are estimated, visualizing the uncertainty is the next important aspect which will make INR-based data analysis more informed and reliable. The choice of selecting appropriate deep uncertainty estimation methods depends on several observations. Firstly, the techniques should require minimal modifications to the existing architecture. This would help to augment uncertainty estimation capabilities in already existing state-of-the-art INR models for scientific datasets. Secondly, the techniques should have a strong theoretical foundation. Lastly, it should not be difficult to implement an INR model with uncertainty estimation capabilities. We picked two uncertainty estimation methods for our study: the Monte Carlo dropout method and the deep ensemble method. We found these two to fulfill each of our considerations. They require very less architecture changes, have strong theory behind them, and they are fairly simple to implement. In both cases, multiple predictions are generated for the same input. The mean of those predictions act as the final prediction, and the standard deviation of those predictions gives us the uncertainty. In Monte Carlo dropout method, using dropout at test time is the key idea. This creates a variation in the model's predictions that is utilized to estimate uncertainty. In the deep ensemble method, multiple models or ensemble members provide their own predictions, and the variation among those is the measure of the ensemble's uncertainty. Here we show the model architecture for both the methods. The input layer consists of 3 nodes for each component of the 3D location vector, and the output layer is a 3D vector. In between, there are multiple residual blocks. Additionally, in the Monte Carlo dropout model architecture, there is a dropout layer at the last residual block. We have presented a study in our paper with dropout layers present at multiple locations in the model and in many different amounts. The ensemble model is the same as the Monte Carlo dropout model, except it does not have any dropout layer. We have trained each of our models for 500 epochs and used the Adam optimizer. For computing the final prediction and uncertainty, 100 Monte Carlo output samples are used. For ensemble methods, 30 output samples are used. We use the mean square error loss to train the model, and for visualization we have used the ParaView software. This is a comparison of volume visualization of ground truth and predicted vector magnitudes for the velocity field of the Hurricane Isabel dataset. The eyes of the hurricane are visually similar in all 3 cases. However, some minor differences can be observed in the area surrounding the eyes. Here we show that the INR model can generate uncertainty-aware streamlines. To visualize the uncertainty present in the streamlines, we create a stream tube visualization. On that stream tube, the diameter varies with the amount of uncertainty present at each point in the streamline. A thicker portion means higher uncertainty. The color also reflects the uncertainty on the stream tube. Next, we can see the stream tube visualization for the turbine dataset. We can observe the uncertainty behavior at different locations in the streamline from the thickness as well as the color of the stream tube. The estimated uncertainty is also comparable for both Monte Carlo dropout and the deep ensemble methods. Critical points are important as flow field features. The left figure shows the LIC visualization of the ground truth vector field for the heated cylinder dataset with the true locations of the critical points. Next, we show the critical point detected by Monte Carlo dropout method and the deep ensemble methods. We observe that both methods detect all the critical points from the INR predicted vector fields. We estimate the spatial uncertainty of each detected critical point. for measuring the spatial variability of each critical point. This helps us to create a variability map, which is shown using the green color as a background. Darker green color behind a critical point indicates that the model has less confidence in the true location of that critical point. As seen for one of the critical points in the Monte Carlo dropout method, you can see a bright green color behind it, which means the Monte Carlo dropout model was very uncertain about the actual location of that particular critical point. In this talk, we have shown that uncertainty visualization can be useful in many ways and provide reliable and unique insights into the flow field data. But there are some limitations as well. These models can sometimes act under or overconfident and give a deceiving measure of their confidence. As can be seen here in the first uncertainty-aware streamline generated from a Monte Carlo dropout model, there is a region of low uncertainty and high error circled in blue. This means that the model is very confident about its prediction, but it is very erroneous. This shows overconfidence. Similarly, on the right side in the red circle, the deep ensemble model is highly uncertain about its prediction, but it is in fact quite accurate. This is a case of underconfidence. This indicates that more research needs to be put into teaching models to assess their confidence properly. To conclude from our comprehensive experiments, we observe that deep ensemble generally gives a better reconstruction quality than the Monte Carlo dropout method. Both methods are often comparable and informative in their uncertainty estimates. Finally, deep ensemble method is computationally expensive. Monte Carlo dropout is a single model approach and hence it can be used in environments which are resource constrained to obtain reliable uncertainty information. Thank you all for listening. I will now welcome any questions from the audience.
Thank you. Okay. That was a great talk. I have a couple of questions about the talk itself, which is first question of volume-based data visualization wise, what are some of the biggest challenges?
Thank you for the question. So I think one of the biggest challenges is most of the volume visualization data are generated through supercomputers, let's say some weather simulations, and storing them seems to be quite a challenge. We're going to store them at a very high resolution. And that is one of the reasons why, as presented in the talk, that the ground truth data may not be available to us because the storage is quite a challenge. So that is one scenario.
Interesting. Thank you. A follow-up question on this is how does it differ from, let's say, what is the difference between 2D and 3D vector visualization apart from their dimensionality? Are there any other considerations that need to be taken care of?
I think some flow features could be simply seen as a 2D flow features. Let's say if you want to see a critical point and you have a 2D vector field, that is possible. But if you want to see streamlines, maybe it's better to have a 3D data set so that you can have some more complicated streamlines.
Got it. Thank you so much. A big round of applause again for Atul and team for the fantastic research. Okay, so we will move on to our next presentation, which is going to be our first short paper of the bunch. And this paper talks about what color scheme is more effective in assisting readers to locate information in a color-coded article. This work has been done by Sam Zeyu, and Ting-Hao Huang, which will be presented by Sam Ying. Sam, take it away, please.
Okay, share the screen. Okay, can you see the screen clearly?
Mhm.
Okay, so good morning, everyone. I'm Sang, the first author of this paper and representing our research team from Pennsylvania State University. Today, I will be presenting our work on the color scheme effectiveness in the color-coded article. And here is the structure of our paper. I will be presenting using this following structure. And first, I will introduce some concept about research objective. Color coding has long been recognized for, sorry, if I was jumping, like, introduction, yeah. Introduction of our paper is like color coding has long been recognized for enhancing reading efficiency and comprehension by clustering information types visually. And with the advancement of LLM models, and we feel that automated document annotation through color coding has become more feasible and potentially making this technique accessible to a broader audience. And however, while the automation aspect has advanced, the specific impact of different color choice on information seeking effectiveness remain underexplored. And so our study aims to bridge this gap by evaluating various color schemes effectiveness in color-coded text document using our LLM. And here's our research objective. And the primary objective is we try to include the following. First, we aim to assess how different color schemes influence the accuracy and speed, which readers locate information in the color-coded documents. And second, we try to understand participant color preference to inform more user-friendly annotation practice. And here the methodology of our study, including the user study design, the color scheme generation, and how we process data and do the label scheme. In this study, we recruit 32 participants with diverse educational background, including master, PhD, and undergrad students, all without visual impairments or color blindness, as they report. And participants were tasked performing time information seeking activity using our color-coded scholarly abstract, which we asked them to identify the first segment of specific label under 8-second time constraint. And we measured two primary performance indicator accuracy and response time. And here is the user interface for testing. At the top of the screen, you'll see a timer, and below there's a legend showing the label and the corresponding colors. And the main section displays the annotated abstract with the text color coded. At the bottom, you will find a question for the current task. For the color coded scheme in this study, we utilize the material UI system and the previous work to generate suitable color combination. And these schemes were carefully designed to adhere to the accessibility standard for contrast ratio, ensuring the text legibility on the screen for information-seeking tasks in our study. And here are the 10 color schemes we generate from a combination of 4 colors. We categorize these schemes into different groups based on the color temperature, such as warm and cool color, and the number of space color used, such as monochromatic and dichromatic, and also the hue similarity, like analogous, which is similar hues, and the non-analogous, which is contrasting hues. And this categorization allows us to explore the effectiveness of the color diversity and the contrast on information-seeking performance. For our data processing and labeling approach, we adopt our previously developed prompt. We have demonstrated high accuracy to process the abstract using recent HCI publication from arXiv. We also employ the label scheme from Pyro research that aligns with the typical structure of academic abstract to categorize the standard statement into different labels. And our finding cover 2 major areas: overall performance across color schemes and the color-specific insights. Our results show that the non-analyzed color, which incorporate contrasting color from different hue range, significantly outperform the analysis scheme in both accuracy and response time. And this suggests that using a mix of contrasting color may enhance information seeking in color-coded documents. Besides, while the dichromatic color schemes utilizing two different base color and enable faster information seeking compared to monochromatic scheme, which use variation of a single base color. And this suggests that incorporating color diversity may enhance the speed of locating specific information in color-coded documents. And we also find that with the yellow inclusive scheme, it not only facilitates quicker response time and also is favored by the participant and indicating the performance and also preference for this prominence and non-distracting nature. In contrast, the red inclusive scheme, which use of the red color inside the color scheme, associated with the longer response time and it also less preferred by the participant. And some participants report that the red color was too bright and distracting and causing some cognitive overload. And here's the discussion from our paper and some takeaway from our study with the following implication, like the psychological impact of color choice and recommendation for effective color choice based on our finding. And first, we feel that yellow emerged as a highly effective color in our study. It demonstrates high visibility, allowing participants to quickly locate information. Moreover, yellow was consistently preferred by users, suggesting a positive psychological response to this color in the content of information-seeking tasks. And red brightness tend to cause more distraction and rather than aid in the information location. And participants also report the longer response time. And red inclusive scheme, which may indicate that the color may not be very suitable for using information seeking. And based on our finding, we recommend some following effective color coding in the test document. First, the mixed color temperature. Combining warm and cool color may enhance the accuracy and speed in information seeking. And the second, we encourage the use of yellow in the color scheme to improve readability and also user preference, making it a valuable component for the annotation practice. And last, avoidance of red. To prevent delay and discomfort, red should be used minimally or avoided in the color-coded document. As LLM advanced in automation document annotation, integrating this finding may lead to more effective and user-friendly color coding system, enhancing information seeking without compromising readability. And here's the summary. Our study demonstrated color scheme selection significantly impact readers' ability to effectively locate information in color-coded documents. And moving forward, we suggest further research into the following: optimizing the color choice for various types beyond the academic paper abstract, exploring the interplay between color coding and comprehension, and also developing colorblind friendly scheme for accessibility. And this is the end of our presentation. Thank you for your attention. Any
Thank you so
question from
much.
the floor?
Thank you so much. Really interesting work on color schemes. And kind of, I was really interested to see that the warm colors takes more precedence than the cold from colors. I do have a couple of questions. First one would be colors kind of based on different cultures mean different things. Although
Yeah.
we're kind of like looking at more preferences to a warmer color. How does your study kind of relate to that question, or do you have plans to study this in the future as well?
Yeah, that's an interesting question because when we are designing this study, we also think about, because at that time why we designed this kind of study is that we feel that the color, many work use the color for text annotation, but they really didn't explain like why they use this specific color. And so that's we try to incorporate studying about the pureness of the color to how they impact the reading performance. And it's interesting that because during the user study, although we didn't try to intend to do like cultural diversity, but as I can recall from our study, the participants actually come from kind of wide range of different culture. And when we are studying, ask them about, because following this performance testing, we also do a short qualitative stuff like by asking them, oh, how you feel, how you think about this study. And most of them feel that like yellow is very useful, red is not good.
Interesting.
And
Okay.
we connect something like maybe in our culture, in Asian culture, we tend to use the yellow highlighter when we were very young. I'm not sure whether it's the same in the US, but we talk some like Indian student, they say, oh, they also have similar stuff. And about the red is maybe every one of us feel like it's not comfortable to read it and bring to brightness. And for a cultural issue, I'm really not have a definite answer, and I'm currently, before you're asking, indeed we didn't see in the color, but I think it would be the interesting question for the future research question. Yeah, I think that's my answer. Thank you.
Sounds good. Thank you so much. Really, really great talk. Let's continue on with our set of presentations.
Thank you.
Next we have a presentation about From Graphs to Words, a computer-assisted framework for the production of accessible text description. This will be presented by Qiang Xu and Thomas Hurtut, presented by Qiang. Qiang, take it away. Thank you.
Can you see the slides?
Mm-hmm.
Okay. Hi, I'm going to present work From Graph to Words, a computer-assisted framework for the production of accessible text description. So to make online visualizations accessible to a broader audience, it's necessary to provide detailed text descriptions so that descriptions can be read by screen readers and users, such as visually impaired people, can form a mental image of the visual content. In our work, we focus on the step of converting a chart to text, and this step presents several challenges. First, we need to know what could be written and what information visually impaired people need to know. Second, we should ensure that the chart is interpreted correctly and that what we wrote is accurate. And lastly, we need to confirm that no essential details are missing and that the description covers all relevant aspects. So in response to these challenges, we developed a framework to help media content creators interpret chart and produce descriptions. To make it easy to use for the target group, we made it compatible with data wrapper. The framework is designed to process a data wrapper chart by identifying key features in the input and generating interactive descriptions of these features with visual linkage. And we will present the framework using a few examples. So the first step is to select an input chart. Users can authenticate with database using a data wrapper token. The chart selection page retrieves visualizations from their account and allows filtering by visualization type, with options to select one or multiple types. And on the other hand, if the user knows the specific chart ID, they can search for it directly. The page displays visualization thumbnails, and clicking a thumbnail activates a preview on the right side. So if the visualization type is supported, the user can click on the select button, which redirects them to the main interface. And the main interface consists of 3 interactive views. There is a list of identified features from the input chart on the left, a section displaying generated descriptions for selected features in the center, and the original input chart with dynamic visual links on the right. And in the next section, we will show 3 specific cases. So the first case is a bar chart about CO2 emission per household by income group. The chart contains general information such as its type, title, subtitle, axis, and color scheme. And the framework dynamically detects and lists these features. Additionally, the chart includes data facts such as individual data points, extrema, mean value, etc. And the framework proceeds similarly with the data facts. So with features listed on the left, users can select any feature to view the corresponding description. The descriptions are generated using templates. For example, for the chart type, the generated description is something like the chart is a bar chart. And for the axis, since the y-axis contains categorical data, the description would be something like the vertical y-axis presents the income quantile and contains the following item, the lower quantile, the second quantile, etc. And the same applies to the colors and to the data facts such as the maximum and the mean value. To interact with generated descriptions, users can hover over the text to see visual links or annotations that show the meaning of the text as illustrated in this GIF. And descriptions can also be edited by clicking on the edit button. And users can reorder them by dragging and dropping them as needed. So that's it for the first case. The second case is group column chart about the education budget. There are two variables presented by different colors, with blue for education and purple for higher education. There are also 6 groups of observations recorded annually from 2019 to 2024. In this case, users may want to compare data across different groups, and to facilitate this, we refer to data in each color as categories and group data, the 6 groups of the observations, as elements. And the feature list will dynamically update, allowing users to select specific variables. For example, for the mean value, if only one variable is selected, the description will present the average for that variable. And if both are selected, the description will present the averages for both of them. The same applies to visual links. If one variable is selected, the annotation will display a single line of average. And with both variables selected, the annotation will be automatically updated to show both averages, as shown in this GIF. And the last case is line chart representing COVID cases. So the chart displays multivariate time series data with red used for Denmark and a darker shade of red for Canada. In addition to the statistical values we have seen before, there are also correlations and trends. So as with previous cases, user can select variables to compare statistical values. They can also view the correlation for each time series. And for trends, the framework identifies relevant intervals of significant variation and highlights these intervals on the chart. To recap, we developed a framework that converts chart to text. The framework is designed for media content creators to facilitate the process of writing and verifying descriptions. And according to participants of the user study, it's useful to see specific information without the need to go to a spreadsheet for calculations. And it not only helps users to determine what to write, but also facilitates graph reinterpretation for deeper insights. For future work, we propose to optimize the template wording. Additionally, we aim to simplify the list of detected features to reduce information overload, because sometimes the chart can get quite complex and the list of features can become really long and it takes a lot of time for users to go over each of the feature. And this can be done by using algorithms to automatically identify significant features or insights. Furthermore, contacting user studies with visually impaired people is recommended, as information preferences may vary depending on different scenarios or stories. So that's the end of the presentation. Thank you for watching.
How does it, a really quick question here, really great talk. One quick question about the visualization types. What are the complex visualizations that are being supported, or do you have plans to extend this to complex visualizations?
So currently it's for basic type of visualization, such as bar chart and its variants. Also line chart, area chart, pie chart. And a group column chart.
Interesting. Thank you. Thank you so much. It was a great talk. Moving on from talk about text description, let's move to our next presentation, which is the design of real-time visual analytics decision support interface to manage air traffic complexity. This work was authored by Elmira, Zohrevandi, Katerina Vrotsou, Westin, Jonas Lundberg, and Andreas Ynnerman, with Elmira presenting.
Hello everyone, my name is Elmira. I'm a postdoctoral researcher in Linköping University, and today I'm going to present the design of a visual analytics interface that aims to support air traffic controllers in managing complex traffic patterns. So an essential task of an air traffic controller is to detect uncertain traffic patterns and predict aircraft future trajectories. This helps them in planning ahead for resolving potential loss of separations. This task, however, heavily relies on controllers' ability in reading the textual information in the labels next to each aircraft. As you can see in the box on the top right, the labels information contain aircraft call sign, ground speed, the rate of climb or descent, and the altitude that the aircraft is currently flying. But the problem is that in denser traffic areas similar to this hypothetical situation shown in this slide, there could be a number of traffic patterns that are prone to cause conflicts. And that's why they are considered complex by the controllers, because it's challenging to detect these patterns, and these patterns impose cognitive load on air traffic controllers. To estimate traffic complexity of a region independent of the sector geometry, aircraft proximity and convergence are usually calculated. Proximity analyzes the aircraft's relative heading and distance and measures their aggregation level. In other words, it measures the maneuvering room available to the controller. But convergence measures the relative velocity between the aircraft and considers the pace at which this aggregation level escalates. So this approach has a shortcoming that I'm going to explain on this slide. So both of these clusters that you are seeing on this slide involve 5 aircraft, which have the same heading and ground speed values. So they have the same convergence. But cluster A has higher proximity because aircraft are relatively closer to each other and leave less maneuver area for controllers. So the limitation of this approach is that a converging pair of aircraft that are mutually in conflict but relatively far is considered less complex by this approach than a pair that are relatively close but not in a conflict. But controllers find a cluster B as more complex because the aircraft that are in conflict are in higher priority for them to resolve. So to address this issue, we conducted an iterative design study to build an interface that supports air traffic controllers in detecting and resolving these complex traffic patterns. The derivation of the interface functions was done through a literature study and discussion with an approach air traffic controller. Then early concepts were designed and I did the prototyping, and then I evaluated the interface with 3 other approach air traffic controllers. And then based on the outcome of that study and another discussion session with 2 other en route ATCOs, the design of the interface was finalized. So now I'm going to present how I designed the concepts based on these derived functions. So a complexity visualization view was designed where complex clusters are detected and visualized in form of circles, and circle diameter represents cluster complexity level. Then the aircraft in a conflict are highlighted in form of a box around their label. And then each aircraft contribution to the reduction of complexity is mapped on 2 spider graphs. The cyan spider graph visualizes aircraft contribution to the complexity with respect to heading variability, and the red spider graph visualizes their contribution with respect to speed variability. And in the next slide, I'm going to explain the design that was done for the 5th function, which is visualizing solutions to the reduction of the complexity. So upon double-clicking on an aircraft in a cluster, a composite glyph appears. In our previous work, we present the design of a glyph that shows solutions to conflicts. So to explain briefly, the blue line indicates the current heading of the aircraft, and the colored sections inside the outer circle indicate the heading conflict zone, and the colored section inside this gray area indicate the rate of climb and descent conflict zone. So the solution space for rate of climb is the gray area inside the inner circle, and the solution space for heading is the white area inside the outer circle. So in this work, we added 2 new encodings that visualize the potential solutions to traffic complexity. So the blue graph here shows the cluster complexity fluctuations, across an 80-degree heading range centered on the current heading. And the red graph here shows the cluster complexity fluctuations across a 40 knot speed range. And this speed box is parallel to the current heading to represent the aircraft velocity. And finally, after discussing the outcome of the study with two en route air traffic controllers, we added an interactive complexity estimation plot that visualizes the complexity of the entire sector for the next 40 minutes. So with this plot, the controllers can prove for a selected strategy how the complexity of the entire sector will be affected for this particular aircraft. So for details on how I calculate the cluster complexity, please read our paper. And with that, I would like to thank you for your attention.
Thank you so much. Really interesting work. Like a complex visualization made more attainable. I have a quick question to follow up the talk. I'm wondering, as you probably mentioned in the paper, there were three air traffic controllers who were involved in the evaluation. Am I correct?
Yes, correct. So it was an initial user study with 3 ATCOs and then a second one with 2 other ATCOs.
Interesting. I'm wondering, because they are very well trained and they're very habituated in looking at the interfaces that they're more familiar with, did you see any challenge that they mentioned that to understand this, or to kind of mention that this is not something that they're used to?
Yes, so it was a non-intuitive design for them in the beginning, but with the visualization support, they could react fast to the complex cluster, and they could ignore the low complexity ones with higher confidence. And they mentioned that they get to learn more about the glyph and the design as they received extra explanations and as they worked with it further. But of course, this can be associated with a steep learning curve, and we aim to do an extensive evaluation study to see which one outweighs the other, the learning curve or the usefulness of the approach in helping them to detect these complex patterns.
Got it. Thank you so much. Really, really great talk. Our last presentation for today, for this session, is going to be building and eroding exogenous and endogenous factors that influence subjective trust in visualization. Work done by Jordan Crouser, Cyril Matosi, Lan Kwang, Saugat Pandey, Owen McKinley, and Alvita Otley, presented by Cyril Matosi for us today. Cyril, take it away.
Hi, can you hear me?
Yep.
Yeah, I'll go ahead and share my screen then.
Please go ahead. Thank you.
Just making sure. Can you see my screen?
Mm-hmm.
Okay. So hi, my name is Ceia Matosi, and today I'm going to be presenting our paper, Building and Eroding Endogenous and Exogenous Factors, that influence subjective trust and visualization. This project is part of an ongoing collaboration between Smith College in Northampton and WashU in St. Louis. So last year's work showed a strong correlation between trust behaviors and the source of a visualization, whether it was scientific or an infographic. However, a student made an interesting observation. The participants themselves didn't know the source of the visualizations. And so this consideration prompted us to find the underlying features of these visualizations that made them more trustworthy. And so how did we find the factors that we want to include in our research? Well, we based ourselves on the existing literature, which shows that human recognizable objects can serve like anchors that increase memorability. Furthermore, the uniqueness of graphs and high data ink ratio increase recall and comprehension. Research also shows that emotions affect cognitive processes like memory, creativity, and problem solving, and that the physiological and cognitive shifts that accompany aging can also affect how people interact with visualizations. This comes usually in forms of visual aids and zoom-in features. So at the end of last year, we left with 3 big questions. 1, what are the specific underlying features of visualizations belonging to different sources that make them more trustworthy? 2, how do the traits of the person viewing the visualization affect what they tune into? And 3, how do both these sets of factors combine to form trust behaviors that we actually observe? So our main goal in our research was to underpin individuals' trust in visualizations. And for that reason, we looked at endogenous factors, which have to do more with visual design, like visualization type, human recognizable object, data ink ratio, and color. We also looked at exogenous factors that have to do more with the individual traits of the person, things like visualization literacy and education. And finally, we want to understand the relationships between these two sets of factors. So it turns out how we define trust is a little complicated. So when you ask someone if they trust something, they're actually answering 5 distinct questions. First, do you understand what this visualization is trying to tell you? 2, are you familiar with the topic of that this visualization is presenting? 3, do you believe the visualization shows real data? 4, would you rely on the facts of the visualization? And 5, would you feel confident using this information to make a decision? And we also included in the slides images of graphs that people did not feel were trustworthy. And so next we want to identify interesting behaviors in our methods and look at the intersection between dimensions of data. However, we have no idea what the underlying shape of the behavior is, and no reason to believe that it's linear or that it moves in a certain direction. That is why we chose a non-parametric approach, like recursive partitioning. The hierarchical approach of decision trees is actually similar to how we think intuitively as individuals. And finally, we use the random forests to make sure that our model isn't overfitting. But here's a question, overfitting what exactly? In our next method, we want to understand this trust phenomenon relative to the individual's baseline. It doesn't make sense for us to compare between someone who was, sorry. It doesn't make sense for us to compare between someone who's fundamentally trustworthy and someone who's fundamentally mistrustful. That's why we want to normalize the person against themselves using the average trust and the standard deviation. We also want to do the same with individual visualizations. And in doing so, we were able to assess the individual's reaction to a given visualization into 3 categories: higher than usual trust, lower than average, and as expected. So now that we divided visualizations and individuals into buckets of higher and lower trust, we can compare them more effectively. And when we look at the individual characteristics affecting trust, we find that the first level, the most prominent, is data literacy. In fact, people with a data literacy that's with a score under 6, is higher. The level of trust for people with visualization literacy under 6 is lower than those with visual literacy over 6. And at the second level, we find that people with associate bachelors and masters have higher levels of trust than those with high schools and doctorates. But when we look at the third level, we find that people with associate bachelor's and master's degree and actually have higher trust when their visualization score is under 9. So these relationships are nuanced and they're not universal. And when we look at visual features, we find that the visualization type is the most prominent among the features. In general, areas, bars, and circles tend to be more trustworthy data visualizations. At the second level, we see that in line with the current literature, visualizations that contain a human recognizable object tend to have higher trust than those that don't contain them. But again, we see that these relationships are not universal, because when we look at the visualizations that have human recognizable objects, we find that although these pictograms are helpful in increasing trust for diagrams and points, that doesn't work with lines, tables, trees, and networks. And finally, we found that both the endogenous and exogenous factors are intertwined and they interact with each other. When we looked at every dimension of trust, we find that mini-score, which is the visualization literacy, and visualization types are coming across as most prominent features in our table. But also, we find that when it comes to every dimension of trust, there are other factors that are bubbling up. And finally, in our future work, our next step is to dig deeper visualization literacy and visualization type. And also, one of the variables that we want to control for in the future is accuracy. In our next work, we want to actually check whether or not the visualization that people trusted were reliable and accurate. And finally, we want to have a more inclusive sample with people at large, not just including people who can use Turk. In fact, our data was collected through online surveys, which requires certain access to internet and knowledge of technologies, and that might be a barrier for older populations. And that's why we want to find more approaches in our data collection. And finally, if there's one thing that I want you to remember out of this presentation, is that if you want to design effective visuals, we need to design for the individuals. Thank you so much.
Thank you so much. Great research on trust visualization and great talk. We have time to sneak in one quick question from the Slido. Daria mentions, what metric are you using to determine visualization literacy? Could you contextualize what Viz literacy less than 6 means?
Could you repeat that? Just like so I'm sure,
Sure.
like, is
What-
it like what?
Yeah, what metric are you using to determine visualization literacy? Could you contextualize what Viz literacy less than 6 means?
So what we used was we have like a certain way of like calculating the score, which is something I can like get more into like later if someone wants to like message me about it. But what visualization literacy, as we mean, is how like familiar are people with like reading visualizations and like their ability to comprehend them.
Thank you so much. A great collection of talks. Thank you everyone for tuning in. If you want to continue conversation, please do so with the Discord channels, or if you bump into each other, feel free to kind of message each other individually as well. I want to thank all the presenters and the audience for sticking with us and listening to us. We are going on a 30-minute break, but after that, we will come back with more interesting sessions. Thank you everyone for tuning in.